If we were to roll a normal fair die a large number of times, what would you expect to be the mean value? Have a think for a minute. What do you think the answer is? Well, let's say we roll the die 600 times. We would expect there to be about 100 of each number. So 100 ones, 100 twos, etc. And so the total value of all of our rolls of the die would be 2,100. Now, to work out the mean value, we need to take that total and divide by the number of rolls, giving us a mean of 3.5 for the 600 rolls. Now, we could have worked this out more easily by choosing a smaller number. So if we rolled a die 6 times, we might expect to get 1 of each number. And then our total would be 21, the number of rolls 6, still giving us a mean of 3.5. But often we're working with probabilities for different events rather than actual numbers of events. So, for example, in rolling the die, the probability of rolling each number is theoretically 1 in 6. So when we're working with probabilities, the way we work out the mean is to multiply each x value by its probability. So in the case of the die, it's 1 times a sixth plus 2 times a sixth, etc., which is 21 over 6 as before, still giving us that answer of 3.5. And the notation here, capital E of x, is used to represent that mean or expected value. Now, when we say expected value, it doesn't mean that we expect to roll 3.5 when we roll a normal 6-sided die. It means that if we roll a die a large number of times, we expect the mean to be 3.5. Now let's look at an example with a bigger sample space. So this time we're throwing 2 dice and we're adding up the totals, so they can vary from 2 to 12. If the total is less than 6, then we're going to receive $5. If it's more than 9, $8, otherwise nothing. We're going to work out what the mean or expected payout per game would be. So we'll introduce a variable, y this time, and we'll say that y is the number of dollars received. So y can be 0, 5 or 8. Now to receive $5, the total has to be less than 6. So the probability of that happening is 10 out of 36. And to receive $8, the total has to be more than 9. So that's a probability of 6 out of 36. And for the remainder of the scores, we receive nothing. So that's a probability of 20 out of 36. Now to work out the expected value of y, which remember is the long-term mean after numerous throws of the dice, we multiply each y value by its probability. And because this is a money scenario, we round to 2 decimal places. So our expected value of y is $2.72. Now remember, we're not going to receive $2.72 in any particular game, because in any particular game we're receiving 0, 8 or 5. But if we play a large number of games, we expect that the mean payout will be $2.72. Now think for a moment, if you were the organiser of this game, how much would you charge somebody per game to play? Remember that if you're organising the game, you do want to make a profit, but you also want to tempt people to play the game. So if they're going to win $0, $8 or $5, you want to charge them an amount that's less than the 8 and the 5, but is more than the $2.72, so that you're going to make a long-term profit, but they will still have a reason to play the game. So a suggestion might be $3. If you charged $3 per game, would the person playing be more likely to win, lose or break even in the long term? Well, the person playing would pay $3, but on average would receive $2.72 per game. So in the long term, they're going to lose. But of course, in any individual game, they might make $2 or make $5, depending if they win 5 or 8. Of course, they could lose the $3. So if you played 100 games, how much money would you expect to win or lose? Well, it would cost you $300 to play those 100 games, and you would make back $272. So on average, you would expect to lose $28. Is it a fair game? Well, if you were the organiser, you'd say yes, and if you were the player, you'd say no. But essentially, a fair game is one where the cost to play equals the expected payout. So it's fair to both sides. Let's have a look at how a ClassPad calculator can help us to find the expected value more efficiently. So because the expected value is really the long-term mean of a probability distribution, we can use the statistics application. Now, if we enter the different values for x in list 1, so in the case of the game with the money and the dice, we could receive 0 or 5 or $8. And if we enter the probabilities into list 2, so that's 20 out of 36, 10 out of 36, and 6 out of 36. Now we can ask the calculator to work with these values. So if we go to calc one variable, x list is the possible values for x, so that's list 1, 0, 5 and 8. And our frequencies are actually in list 2. So although it's called frequency, really these are the probabilities when we're working out the expected value. Okay, and the top figure there, the mean of x, is the expected value for the distribution, 2.72, as we would expect. Also, further down the list you can see we've got the standard deviation, 3.19 in this case, and you can scroll down the list to see other statistics that may or may not be useful.